All right then, so let's begin with the derivation of the conservation of linear momentum equations. So this first sequence of videos is going to be quite dry, to be honest. It's very mathematical. It's essentially just a long derivation of the aircraft equations of motion. But it's very important that you know where these equations come from and know how the assumptions that we've made allow us to derive these equations for describing the flight of an aircraft. So please try and stay with me. I'm going to do my best to explain these derivations as best as I possibly can. So what's also become tradition on my online videos is that I like to discuss my daily beverage of choice. So today we're on the Arizona sweet tea, which is a particularly good one, particularly if you are in need of a bit of caffeine in the morning, as I am this morning. But ultimately I think I prefer the raspberry one. So let me know your thoughts on the best Arizona iced tea. So we begin our derivation of the conservation of linear momentum equations with the basic definition or expression of Newton's second law, F equals ma. Hopefully very familiar to all of you. Then what we can say by the product rule is that we can write the derivative with respect to time of mass times the velocity vector is the derivative of, so we do this multiplied by the derivative of this plus this multiplied by the derivative of this, right? That's just a product rule. And we've said that in our assumptions we're going to assume that for short periods of time during flight the mass of our aircraft is going to be constant, so dm by dt is going to be 0, right? The change of mass with respect to time is going to be 0 by assumption, so that we're just left with this term here, and we can write the derivative of velocity with respect to time as just acceleration, right? So we're just left with this expression here. Now, in order to define what goes into our force vector here, we need to think about the forces that are actually acting on our aeroplane. So we have three different types of force that are acting on our aeroplane in flight. We have gravity, obviously, and that's a volume force, right? Because it's proportional to the mass of the volumetric elements of the aircraft. And we also have thrust forces and aerodynamic forces, which we describe as lift and drag, right? And they're both surface forces. One other thing to note is that how we can describe mass of our aircraft. So if we consider little infinitesimal chunks of our aircraft, which each have a density associated with them, right? And we integrate that over the whole volume of the aircraft, that gives us the total mass of the aircraft, right? So this is just a different way of expressing m due to the different densities of the materials that make up the aircraft. So what we're able to do using those two bits of information is to rewrite Newton's second law in this form here. So this is basically our mg term, right? Mass times gravity. So we said how we describe mass here as the integral of rho a with respect to v. So g is our gravity vector, so this is mg. This is our two other forces, so this is our two surface forces, the aerodynamic forces, lift and drag, and the thrust forces from the engines or power plant or whatever. And then this is our right hand side, so this is the derivative of, so this is how we described acceleration, right? This derivative here multiplied by mass again, right? So F equals ma. So the next thing we need to do is describe Newton's second law in terms of a particular axis system, which describes where our aircraft is. So this is an arbitrary chunk of our aircraft, look, which we're describing. This has mass dm, it has surface or shape ds, and it has volume dv. And then we can describe these vectors which relate it to two different types of reference system. So the first thing we're going to do is derive the conservation of linear momentum with respect to the Earth axis system, and then extend that to the body axis system. So there are some vectors here which relate our chunk of aircraft to both of those axis systems. So first of all, we're going to consider this vector here, r bar dash, which relates our chunk of aircraft to the origin of the Earth-based inertial frame, which has axes capital X dash, capital Y dash, capital Z dash. And you can see that this vector here is the sum of this vector, which relates our chunk of aircraft to the aircraft center of gravity, which is going to be the origin of our body axis system, and this vector here, r bar dash sub p, which relates the origin of the body axis system to the Earth-based inertial system. So this is figure 1.1 from the textbook, and we're going to use that to describe Newton's second law with respect to the Earth axis system. So this is the vector which relates our little piece of aircraft to the origin of the Earth axis system. That's the sum of those two other vectors as we've just discussed. And the derivative of a position with respect to time just gives us a velocity, right? So what we're able to do then is write our previous equation, this one here, and rewrite what we're calling this vector v here. So the left-hand side stays the same, and then we have d by dt. We've replaced v by this expression here, which just comes from this, and that just gives us the second derivative of r bar dash with respect to t. And we're going to call that equation star because we're going to use that again in a moment. So we also know that the body axis system has its origin at the center of gravity, as we've just described in this figure, right? The center of gravity is here. That's going to be the origin of our body axis system. And because the origin of that axis system is at the center of gravity position, if the aircraft is in trim, then the net moments about that point are 0. So if this r bar relates the chunk of aircraft that we're interested in to the center of gravity position, then the net moments about that point are 0. So that means that we can write this, which describes our moments, right? So the moment arm multiplied by the mass at that point, right? Remember, mass is described as the integral over v of rho a dv. So that's the moment arm multiplied by the mass. So we can say that the net moments about that point are 0. And then because we know that this vector, which is the one describing the distance between the chunk of aircraft and the Earth axis system, is equal to the sum of the others, then we can rearrange that for r bar like this. And so this equation we can rewrite just as the difference between r bar dash and r bar dash sub p. Right, so the next step is we can take this part here, which we're equating to 0 because of this fact here, split that integral up into two pieces, and then because the difference between these two integrals is 0, we can equate them to each other, and then rewrite the right hand side by taking r bar p dash out of the integral to leave this, and this is what we're calling mass, right? So if we take both ends of this equation, we can divide the left-hand side through by m to get an expression for r bar p dash, like that. So by following exactly the same process, we're also able to rearrange this equation here, which we called star, right? So we have this r bar dash in this right-hand side here. So again, we can use this vector here, the sum of the two other vectors, to rewrite this part of the equation, which is what I've done here. And then again, we can split this up into two separate integrals, like we did just now for the other part of the equation, to leave this, the sum of these two integrals. And then we already know that this is equal to 0 from our assumption that the net moments about the center of gravity are 0, right? So again, this is the moment arm, this is the mass, and we're assuming that's 0. So we're just left with this piece here, which again we can rearrange by taking out the vector rp bar dash from the integral, leaving us just this piece here, which again is mass. So rearranging that a little bit, taking m out of that, because again we're assuming that m doesn't depend on time, we get the second derivative of rp bar dash with respect to time, the second derivative, which, as we said previously, the derivative of a position with respect to time is just velocity. So we have this. So what we've done is, if we put all of those bits together, we've got our F here, which is the sum of the gravity forces, aerodynamic forces, thrust forces, equals ma, which we have just derived with respect to the Earth axis system. So here, v bar sub p is the vector relating the velocity of the body axis system with respect to the Earth axis system. So the final step of this derivation of the conservation of linear momentum equations is to write them with respect to the body axis system. So remember, we just wrote them with respect to the Earth axis system. Well, in order to write them with respect to the body axis system, we need to consider the angular velocity of the body axis system with respect to the Earth axis system, right? Because it could be twisting. And we describe that angular velocity with the parameter omega, lowercase omega, right? So we can rewrite our equation here from the Earth axis system like this, where the left-hand side stays the same, but on the right-hand side, here we have this term which describes the rotation of our vector field, right? So remember or recall the operator curl from vector calculus, right? So that describes how the body axis reference system is rotating with respect to the Earth axis system. And for convenience and for neatness, we start writing our derivatives, our partial derivatives, with respect to t, just with a dot. So this is just equivalent to this, where I've just written this partial derivative with respect to t as a dot. So now we're going to define the components of each of these vectors, right? So we've got a g vector, an fa vector, ft, and so on, right? And we're just going to define the components of those, where I bar, j bar, and k bar are the unit vectors in the X, capital Y, and capital Z directions, which is the body axis reference system. So, for example, we write our velocity vector v sub p as components u, v, and w, and so on. So what we can do, having defined these components, is work out what omega cross vp is. So remember how to do a cross product, we just take the determinant of a 3x3 matrix in this case. So omega has components p, q, and r. Vp has components u, v and w. We take the cross product to find the following expression. And that allows us finally to write the conservation of linear momentum equations with respect to the body axis reference system, where I've split these up into components, right? So I've taken all of the I bars, all of the j bars and all of the k bars, and written the conservation of linear momentum equations out in component form. So that completes the derivation of the conservation of linear momentum equations. We'll now move on to look at the conservation of angular momentum equations.